Okay, so Newton's third law tells us that whenever one body exerts a force on a second body, the second body exerts an oppositely directed but equal force on that first body. So let's have a look at a few examples of where we can see Newton's third law in action. Okay, so in this example, there was a tennis ball which exerted a force on this paddle. You would have experienced this if you ever played tennis. Whenever you make contact with the ball, you'll feel the force acting on the tennis racket. So the ball's exerting a force on the paddle, and at the same time, the paddle is exerting a force on the ball. So in this case, the paddle was exerting a force towards the camera, going forwards out of your screen, and the ball was exerting a force pushing the paddle backwards. These two forces were equal in magnitude, but opposite in direction. Okay, another example you can be seen with this balloon. Okay, so I'm going to let go of this balloon. When I do that, the air rushes out of the balloon. So the balloon is applying a backwards force on the air, and at the same time, the air is applying a force on the balloon, forcing it to go forwards. So the air rushes out and the balloon rushes forwards in the opposite direction. In this case, these two forces are equal in magnitude, but opposite in direction. This is Dr. Julian Berengut, who's a theoretical physicist in the School of Physics. He's going to help me demonstrate Newton's third law. So what I'm going to do is I'm going to pull on this rod here. Can you predict what's going to happen when I pull on the rod? Okay, here it goes. So did you predict that we'd both move? Newton's third law tells us that when I apply a force on this rod, then the rod applies an equal and opposite force on Julian, moving us both together. Now look at what happens when I push off in the opposite direction on the rod. We both start to move apart.
Okay, so an example question. A man with a mass of 80.0 kilograms pushes a car with a mass of 2,000 kilograms. Assume that there is very little friction preventing the car's movement. The car accelerates at 0.30 meters per second. 1. What force does the man apply to the car? 2. What force does the car apply to the man? 3. Why doesn't the man move backwards? Okay, so in part 1, we'll need to use Newton's second law. So we know that the sum of the forces is equal to ma. So in this case, the only force involved is the man pushing on the car, because we're told that there's very little friction, so that's basically telling us that there's no other forces. So this is equal to the force of the man on car. And so we're trying to work out what this is, so it's equal to ma. And we're told that the mass of the car is 2,000 kilograms and that the acceleration is 0.30. And so this is equal to 600 newtons. And it's in the direction the man pushes. So now in part 2, it asks, well, what force does the car apply to the man? So when the man pushes on the car, Newton's third law tells us that the car is going to push on the man with an equal and opposite force. So we could draw a little diagram here. Here's our man, here's our car. When the man pushes on the car with this force, then the car pushes on the man with the same force, same magnitude, but in the opposite direction. So F of car on man is equal to minus F of man on car. So this is equal to 600 newtons in the direction opposite to the one the man pushes in. Okay, So part 3 then asks us, well, why doesn't the man move? Okay, so if the man's not moving, here's the man, and we know that we've got this F of car on man here. So this tells us that there must be a force to balance this force. So there must be a force pushing the man in this direction. So what force could that be? Well, that must be the frictional force. So the frictional force from the ground on the man must balance the force of the car on the man. So part 3, there is a frictional force and it's pushing the man forwards, which is equal and opposite to the force of the car on the man, and hence the man does not move.